Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture on transport phenomena. What we will do is start with an example, and that is very similar to what we discussed yesterday, the laminar flow, but extended to system where we have two phases. Okay. Then we will start with some abstract concepts which we will use later on in the course, rather than start the very first lecture with abstract concepts, so you can understand things better. Okay. So, our topic that we are going to discuss is basically microfluidics. Okay. What I will do is one of the advantages of using this microfluidics is, the particular problem that we are going to talk about is stratified flow in two phase systems. The two phases that we are talking about are basically two immiscible liquids, oil and water. Okay. So, we have oil and water which are being pumped in, maybe an organic phase and an aqueous phase, you are pumping it, and stratified flow means the two liquids are flowing side by side. Okay. So, the two liquids flow side by side. If you look at the thing from the point of view of hydrodynamics, I will classify these as one dimensional flows, okay, which means there is only one velocity component, the other two velocity components are 0, and this one velocity component which exists is varying in one spatial coordinate. Okay. So, this is going to be, these are called one dimensional flows. Okay. Only one velocity component is present and it varies in one spatial direction. Similar to what you see in laminar flow, you have only the axial velocity which is varying in the radial direction. If you have laminar flow in a pipe, that is like a one dimensional flow for me. Vz, the axial velocity component, varies in the radial direction. Okay. So, here this is laminar flow has axial velocity varying in the radial direction. So, that is the, so we are extending whatever you know about laminar flow for single phase to two phase problems. Okay. So, hydrodynamically these are what I call one dimensional flows. Now, what is the motivation for doing microfluidics? First, what is microfluidics? Okay. So, if the characteristic dimension is less than 1 millimeter or 1000 microns, we have a microfluidic system. Okay. So, if the diameter of your tube through which is flowing is half a millimeter, that is about 500 microns, that is a microfluidic system. So, that is the classical definition of microfluidics. Okay. So, now there are lots of reasons for people to explore this area of microfluidics. If you had read the newspaper maybe 2 days back, you may have seen that in Bangalore the innovation hubs, the startup hub, there was a big accident. About 100 crores worth of infrastructure were destroyed, because these were startups which were basically handling chemicals, okay, and there were some solvents they were using, and that basically were inflammable, that caught fire, and it destroyed a lot of things, okay. So, basically in the chemical process industries, you are handling chemicals, and it's if you are handling large volumes, you will have a problem with accidents. For example, if your chemicals are toxic, they may have a health hazard, okay. So, one of the advantages of microfluidics is you are dealing with small volumes of chemicals, okay. So, when it comes to handling hazardous chemicals, when it comes to handling toxic chemicals, it is safer for you to do things with microfluidics, okay. So, that is something which I wanted to start with, saying that this helps in handling toxic chemicals and hazardous chemicals, since the inventory is low or small. If you want to ask questions, you can ask questions, that is not a problem, okay. Just because it is being recorded does not mean you cannot ask questions, you can ask questions. So, that is the one of the advantages, okay. The other thing is, since you are talking about very small sizes, small volumes, small pipes, the surface area to volume ratio is very high, okay. So, because the surface area to volume ratio is very high, this has very good heat transfer characteristics. So, if you want to conduct an exothermic reaction, whatever heat is being generated by the reaction can easily be lost to the environment, and the temperature will be controlled, okay. If you want to do it in a big reactor, then the rate at which heat is being generated is much higher, heat loss will be less, okay. So, there is a likelihood of a runaway reaction, an explosion or something like that happening. So, to carry out exothermic reactions, the microfluidic setup is very useful, okay. So, this can be used to carry out exothermic reactions, because here the surface area to volume ratio is high, and the heat generated is lost efficiently to the ambient. So, if you look at things like nitration of benzene, nitration of toluene, which are basically used nitrobenzene, trinitrotoluene, these are explosives. So, the manufacturing of these are extremely exothermic. Okay. So, you could do this kind of manufacture safely because the kind of volumes that you are dealing with is less, okay, and the heat transfer characteristics are good. So, this is very safe to use microfluidics where your channel dimensions are very small, okay, for these kinds of problems. Okay. So, here this is a safe way to carry out these reactions. Okay. So, the way they do it is that, so the question is it economical to do microfluidics? Okay. So, one has to do an analysis, but the way you do large scale production is by doing what is called numbering up. You do a parallel processing, you have lots of these channels which are going to be modular. Okay. So, the advantage is if there is some problem with one particular module, you just throw that module out and the rest of the modules are still working. So, imagine a plant where you have all these small micro channels, okay, in parallel, and they are going to be, each is going to be working like a reactor with these kinds of characteristics. So, this is called numbering up. Okay. So, rather than have one big plant, you have lots of small plants operating in parallel. Okay. That is how you try to increase the scale of production. Okay. And advantages are, like I said, is modular. So, some problem with one module, you just throw it, plug in another module which works. Okay. Otherwise, you have to go for an entire plant shutdown, okay, then fix the problem and start. But here you do not have to do that. So, of course, you have to analyze. You may not be able to use microfluidics for anything and everything. So, but I am just telling you certain things for you to think of, and then you can sit down and look at whether for your particular problem microfluidics is the way to go. For example, pharma products, your scale of production is usually small. So, that may be a good option. So, okay. So, now like I said, there can be, it is not that microfluidics always is the solution to all of life's problems. For example, if you were to carry out nanoparticle synthesis, okay, when you are trying to make nanoparticles, our objective is to try and get particles of a uniform size. So, they are monodisperse, okay. You do not want a size distribution. So, that is the objective, but in a microfluidic system, especially for laminar flow, we have a distribution of residence times, which means the fluid element which is flowing through the middle is going to have a higher velocity, okay. So, it is going to spend less time in the reactor, in your microfluidic channel, which is your reactor, which is where the synthesis is happening. So, that guy is spending less time. The fluid elements close to the wall, they are going to be spending larger time because the velocity is lower there, because as you go closer to the wall, the velocity is tending to 0, okay. So, there is a distribution of the time spent by fluid elements in the reactor, and what this means is your output product may have a particle size distribution, okay. You may not get a monodispersed particle, for example. Okay. So, this implies we may not get a mono dispersed particle size. Okay. This could be a problem because that means your quality of your product is bad. If you want to do some synthesis of a polymer, for example, again polymers are characterized by their molecular weight. Okay. And you again want to have as far as possible molecular weights of only a fixed number. Okay. You do not want a molecular weight distribution. So, if you want to carry out a polymerization reaction, you might have a molecular weight distribution. So, my point is, even if you do not do, you are thinking of doing a polymerization reaction, you can use your learnings from nanoparticle synthesis or vice versa. So, there may be literature in polymerization which talks about molecular weight distribution. You may be interested in nanoparticle synthesis. So, whatever learning is there from polymerization, you should be able to use it for nanoparticle synthesis, for example. Okay. So, I mean, and you can do that only if you understand the fundamentals about what is happening. It is, you cannot think polymerization is completely different from nanoparticle synthesis. The cause of the problem is the same, the residence time distribution. This is where the fundamentals are important. Okay. So, this is also true if we carry out a polymerization reaction. Here we get a molecular weight distribution, and the cause for this is the same in both the systems. Okay. So, same both examples. Okay. So, that is the thing which you need to keep in mind. Okay. When you do a problem, try to understand the basic physics. So, basically as far as this particular course is concerned, is a lot of physics, a lot of mathematics, that is all you have. Okay. And we use physics to analyze specific problems, mathematics to get solutions to the problems that we have. Okay. Now, what I want to do is talk about the stratified flow problem. Okay, look at the hydrodynamics, and then we will proceed further. But this was just to motivate why microfluidics is important. Okay. What is the geometry we are looking at? We are looking at stratified flow. Okay. So, you have oil, and let us say you have water coming in here, they are being pumped. Okay. I have, so this is a T shaped channel, this looks like a T, right, a T which is rotated. So, this is a T junction, oil is being pumped there is another pump which is pumping in water. So, the two liquids will come, they will flow, and this is water and this is oil. okay. We are looking at things from the top. The tea is lying on the bench, on the desk, and the two fluids are flowing side by side. We are looking from the top, okay. Now, yeah, so when this happens, I can divide this entire channel into two portions. The first portion near the inlet, this is where we have the entrance effects, okay, because that is near the inlet for the channel. Far away, this is what we call the fully developed region. So, right now I am assuming we have stratified flow, okay, and so that this is assumption we are making. We are assuming we have stratified flow for a particular combination of liquids, for a particular wall, for a particular flow rate, okay, and then we are proceeding to analyze. So, now in an actual system, the entrance region may be very small compared to the full length. So, if you are carrying out a reaction or an extraction or something, the main process is going to happen only in the fully developed region. In the entrance region, which is a very small region, you can neglect, okay. So, then you are focusing only on the fully developed region. But if you have a situation where you say no, I am interested only in the entrance region, I want to figure out how much time it takes, then you possibly have to do a numerical solution, okay, use some of these CFD softwares to understand how the flow is developing in the entrance region, how are things changing, okay. So, in the fully developed region here, in the fully developed region, flow does not change along the length, okay. And since we are interested in analytical solutions and trying to understand what is going on, we are going to focus on the fully developed region, okay. So, that is our focus, because the fully developed region is going to occupy a major portion of the channel, okay. So, our focus is here to find the entrance region flow. You need something like CFD, for example, okay, and that is not what we are going to do, that is not the objective of this course. So, I mean, when you are solving a problem, you need to understand what are the assumptions you have made, and as a result of which, when you get some results, you should know what the limitations are, okay. So, tomorrow when you have some challenge with analyzing the results, you may have to come back and look at the assumptions. Are the assumptions the reason for these results which are unexpected? Then you can come back and change the assumptions and rework the problem, okay. For example, I am assuming that the fully developed region is dominant. Maybe you have some system where the entrance region is dominant, the fully developed region is not dominant. So, then you have to come back and use CFD, the analytical solution that I am giving is useless, okay. So, what I am saying is, please you got to understand physically what is happening, and that will help you interpret your results properly, okay. So, now I am going to assume that you know equation of continuity and the Navier-Stokes equations. We will derive them later on in the maybe next week, but so the actual problem will have a rectangular cross section or square cross section or a rectangular cross section, okay. But since I am interested only in one dimensional flows where things are going to vary only in one spatial direction, okay. So clearly in the fully developed region there is going to be no variation in this, in the direction of the flow. That is the meaning of fully developed, okay. So we are going to have variations only in this direction, in the perpendicular direction, because it has to satisfy the zero velocity boundary condition here, the no slip condition, and the velocity will be larger as you go towards the center. So velocity will vary in that direction. That was what we said we will do. We will look at one dimensional flows, okay. So to understand things we are going to make some assumptions, okay. I am going to look at this is the x direction, this is the y direction, and I have the z direction which is perpendicular to the board, okay. And I am only interested in the fully developed region, I am not interested in the entrance region. So I am only focusing on what is happening here, okay. That is the thing I have drawn, and what I have is, yeah, x and y, and let us say this is liquid 1. So this has properties mu 1, rho 1 and V1, this is mu 2, rho 2, V2. What are these? This is the viscosity, density of the second fluid and the first fluid. So rather than talk about oil and water, I am just calling water first phase, oil second phase, okay. So the viscosities, densities, velocities are going to be different. Now what we want to do, how do I make things what are the assumptions because of which my fluid is actually one dimensional, the flow is one dimensional. I am going to assume that the channel tends to infinity in the z direction, okay. So basically what this means is, it's like two plates, okay. This wall is like a plate which is extending to infinity, this wall is extending to infinity. So we are focusing somewhere in the middle in the z direction. So there are no boundary effects which are going to be felt, okay. And this implies W, the z component of velocity is 0, and also d by dz is 0, okay. So this is an assumption we are making for the purposes of trying to get a grip of this problem, okay. So in the z direction things are infinitely long, and our flow is basically going to be in the xy plane. There will be variation in the y direction because it has to satisfy the no slip boundary conditions, okay. And the flow is in the, this is what I said, we will have only one velocity component varying in one spatial direction. So basically I am giving you the answer right now, but we will see why, how it is coming, okay. So here we have only the x component of velocity varying in the y direction, the one dimensional flow, okay. That is why, so that is this thing right now. We will have to see why the other components are not present, okay. See, when you are solving a problem you can't keep assuming, oh v is also 0, the y component is also 0. You have to make minimal assumptions and try to get maximum information, otherwise you keep assuming everything, then there may be contradictions, you may be doing something wrong, okay. So whenever you are solving a problem you have to make minimal assumptions, okay. So, the only assumption I am making here, this is the result, only assumption I am making is infinite channel, and because infinitely long, if I look at it from this, look at it from xy plane, I see the flow only in this direction, there is no variation in the z direction. Okay. So, let us use the conservation of mass for this problem. No, before that, before we do this apply the conservation of mass, what is it that we are interested in analyzing? So, before you solve a problem, you should be curious. I mean, if it is an exam, okay, I have given you a problem, so you have to solve it, you do not have any other go. But supposing you are doing a research problem, I mean, when you start embarking on a research problem, there are some questions you have to ask, right. So, in this particular system that we have, what are the questions that we are going to ask? Okay. Any idea? Any suggestions? Okay. Yeah. Yeah. What are the questions we choose to answer? Yeah. So, the first thing is velocity profile. Not what determines, what is the velocity profile, right. Velocity profile. Okay. The other question which you may be interested in is trying to relate, okay, the volume fraction occupied by each phase to the flow rate fraction that you are pumping in. Okay. So, for example, the relation between volume fraction in the channel to the flow rate fraction. What do I mean by that? Supposing the flow rate of this liquid is Q1 and this is Q2, okay, and this entire channel distance is capital H and this guy is small h. So, small h is the thickness occupied by the first fluid, capital H is the total thickness, Q1 is flow rate of first liquid, Q2 is the flow rate of the second liquid. Now, if you are pumping two liquids the same flow rate, will the small h be capital H by 2, will the volumes occupied by both the liquids be equal? I am pumping two liquids at the same flow rate, okay, and because the flow rate is the same, the question is, are they occupying the same position, same fraction in the channel. So, basically what I am saying is, we want to find a relationship between Q1 divided by Q1 plus Q2 and relate that to H by H. It should be the other way. I think I put the function on the wrong side, because why should the function be on the left hand side? Because that is the thing which I can control experimentally, that is my independent variable, okay. Small h, the interface is not something which I can control as an experimentalist. As an experimentalist, I can only control the flow rate that I am pumping in. H is my dependent variable, small h is my dependent variable. So, I want to write small h by h as function of this, okay. So, now this is something. So, basically if Q1 equal to Q2, if for example, if Q1 equals Q2, is H going to be equal to H by 2, okay, because the volumes occupied by each phase is going to determine the residence time in the channel, and that will decide if you are doing a reaction, is it going to be efficient, not efficient. Okay. So, we have interest in finding out this volume fraction, which is called hold up. Okay. So, I mean this volume fraction on the first phase is called the hold up of the first phase, for example. So, H by H, volume fraction of phase 1, which is called the hold up of phase 1. Okay. So, I mean, whenever you solve a problem, you have to be clear about the goal. Okay. I mean, especially if you are doing research, it does not matter whether it is fluid mechanics or anything that you want to do. So, now we come to conservation of mass. So, since we are talking about fluid flow, the conservation of mass is going to be given by the equation of continuity in the differential form. Okay. So, here for fluid 1, I am going to write d rho 1 by dt plus divergence of rho 1 v 1 equals 0. Okay. Now, all of you have seen this equation before? Yes? No? How many have not seen this equation? Okay. So, I am going to assume you all know this equation, we proceed. Okay. So, this is basically, this is called equation of continuity, conservation of mass. Okay. And I am going to assume my fluid is incompressible. Okay. That is a reasonable assumption, which means the density does not change. Okay. So, if the density does not change, I can assume rho 1 does not depend upon x, y, z and t. So, rho 1 is constant, rho 1 equals constant. What is rho 1? Density of the first liquid, it could be water. Okay. I get divergence of V1 equal to 0. So, that is what it is. Okay. I must be careful, so I am going to put an arrow mark here to tell you that this is the velocity vector. Okay. And I am going to now write this divergence in this full form, which will be du1 by dx plus dv1 by dy plus dw1 by dz equal to 0. That is your divergence for the vector. Now, u1, v1, w1 are the velocity components, okay, without the arrow. So, if I put the arrow, it is a vector. So, this is the vector, this is the x component of velocity, the y component of velocity, z component of velocity. Okay. So, now because of this infinite plate assumption, okay, I have W1 equal to 0 and dou W1 by dou Z equal to 0 because of infinite plate assumption. Okay. We are also focusing only on the fully developed portion. Fully developed portion means in the x is the direction of the flow. So, things are not changing, the velocity is not changing in the x direction. Okay. So, that means what? There is no change in the u1 in the x direction. So, this is fully developed flow. Okay. Because of the, I am not making an extra assumption here, I have assumed fully developed, I am focusing only in that region, I am assuming incompressible, so the density goes off, and flat plates. Now, so what is the, from the equation of continuity, I get dV1 by dy equal to 0, okay. My equation of continuity is simplifying to this. So now, it means V1 is not a function of y, that is the only thing I can conclude, okay. V1 is not a function of y, okay. Now, the two walls that I have, they are rigid walls, let us say, okay, they are plates. So, the liquid cannot penetrate the wall. So, this is y equal to 0, small h, this is capital H. So, this is a solid wall, both are solid walls. So, the liquid cannot penetrate my solid wall, okay. What does that mean? That means the V1 at y equal to 0 is 0, okay. Therefore, this is the no penetration condition. So, V1 at y equal to 0 is 0. So, everywhere here, because the liquid cannot penetrate, the vertical component of velocity V1 is 0, okay. So, V1 is 0 at this particular y, V1 does not change in the y direction, and therefore, I conclude that V1 does not change, V1 is 0 everywhere, okay. Therefore, V1 is 0 everywhere, okay. I am not assuming V1 is 0, I only made two assumptions, fully developed, I only assumed infinite plates, infinite wall, okay, in the z direction. So, V1 equal to 0 is not an assumption, it is something, it is coming out from those two assumptions, okay. So, like I said, make minimum assumptions, do not make, you assume everything, then what are you going to solve for, okay. So, that is what it is. Now, you can make a similar argument for the second fluid. Second fluid again we will assume incompressible. Now, I will impose the boundary condition at the other wall, because the second fluid is exposed to the top wall, okay. For second liquid, we can show V2 is 0 because the top wall, whatever the top wall at y equal to h is solid and V2 at y equal to h is 0, okay. So, I mean I am not going to do it, it will be just a repeat of whatever I have done, simplify the equation of continuity, make the same arguments, W2 will be 0, fully developed. So, only dV2 by dy will come equal to 0, and because velocity is 0, it will be 0 everywhere, okay. So, basically what this means is W2 is 0 because there is no flow happening in that direction, V is 0, so only one velocity component, that is what I said we will have. So, this is the example of the one dimensional flow. Now, we have to find out how does the velocity change in the y direction, okay. So, for that we need to go to the momentum balance, and that is what we will do. You are used to again Navier-Stokes equation, and the direction is again a momentum balance we are looking at. The interesting one is the x momentum, because the flow is in the x direction, okay. The flow is in the x direction. So, I did not know there was a clock here, so I just had this thing to tell me to stop, okay. So, okay, so let me write down this x momentum balance. We are looking at x direction, velocity component is u, microchannels minus gradient of P plus mu del squared U1, okay. So, this is the momentum balance in the x direction. X direction, remember, is the horizontal direction. So, I am not even considering gravity, okay. This all flow in the horizontal direction, no gravity is coming into the picture. So, this is my pressure and I am going to put this as P1, okay. This is mu1 because the first liquid can have a different viscosity compared to the second liquid, mu1 del square u1, and this is what it is. Now, this Navier-Stokes equations in general are non-linear. Which is the term which is making it non-linear? If you remember the math course which we taught, which we went through some few days ago, these are the terms which make it non-linear, because you have the dependent variables u1, v1, w1 are the dependent variables, they are not known, you have products of those variables, okay. So, in general, because these equations are non-linear, the solution is usually a challenge, okay. The reason why Navier-Stokes equations are difficult to solve in realistic cases are because these are non-linear in nature. If equations are linear, because you did this math course last semester, you will all be experts in solving linear equations, right, separation of variables, what else, Green's functions, whatever it is. So, now let us, so I want you to go over the weekend and see on the basis of whatever we have derived so far, if you can simplify this equation. What will be the simplified equation? You do it, I am going to do it in the class on Monday and then we can compare, okay. So, do that for this x momentum, you can do it for the y momentum and the z momentum. Z may be not required, just x and y momentum, because those are the two directions which are of interest to us. Simplify the Navier-Stokes equations in the x and y direction, and I will do that and then we can see what we get, okay. Thank you.